Good day, colleagues. Today, we are diving into a scientific inquiry lesson designed to challenge our macroscopic assumptions and force us to look closer at the molecular reality of solutions. We call this a 50-50 paradox. It serves as an elegant case study of how the immediate, visible world can sometimes mislead us, and how fundamental scientific inquiry forces us to peer deeper into the underlying particulate nature of matter. Before we begin the investigation, I want to formally attribute this inquiry framework. This lesson and presentation were developed by Sampadi Tonga from Shakwaneng Primary School, located in the Bolabella district of the Mpumalanga province. Let us begin. The standard textbook rule. Let's start with what our foundational textbooks teach us. The standard rule states, in a solution, the solvent is a substance present in the greatest amount. The solute is a substance that is dissolved. For the vast majority of introductory science scenarios, this majority rule works flawlessly. If you drop a spoonful of salt into a glass of water, water is a majority, so it's the solvent. If you pour a shot of espresso into a cup of milk, the milk is in the greatest amount, making it the solvent. It's clean, simple, and intuitive. Macroscopic observation. But science thrives on testing the limits of our rules. Let us look at step 1 of our inquiry, macroscopic observation. Suppose we take exactly 50 milliliters of water and mix it with exactly 50 milliliters of acetone. When they meet, they exhibit perfect miscibility. They do not separate into layers, they do not form a phase boundary, and they do not repel one another. Instead, they completely blend to form a single, uniform 100 milliliter solution. And this is exactly where our textbook rule breaks down, and we hit a 50-50 deadlock. Consider the criteria. Both substances are liquids. Their initial volumes are dead even at 50 milliliters each, and absolutely neither substance holds a macroscopic majority. So, we face an anomaly. Based strictly on the standard rule, greatest amount. Which one is a solvent, and which one is a solute? We have a tie, and the rule leaves us at a standstill. Why the perfect mix? To guarantee that this isn't an optical illusion or a temporary state, we can visually prove this perfect mix. If we take our acetone and add a red dye, and take our water and add a blue dye, their combination doesn't result in a striated or separated liquid. It creates a completely unified purple solution. The distribution of properties is thoroughly uniform across the entire volume. The invisible handshake. What is driving this macroscopic miscibility? The answer lies in what we call the invisible handshake, driven entirely by microscopic polarity. Water is a highly polar molecule featuring partially positive hydrogen atoms. Acetone, on the other hand, contains a carbon skeleton but features a highly polar oxygen atom. This specific alignment allows them to form hydrogen bonds. They quite literally shake hands at the molecular level, integrating perfectly despite their differences. So how do we solve the problem of the Eastern Cape? Ha! 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 Mr. Magwin Chu. This brings us to the limit of the lab bench. Volume is purely a macroscopic measurement. It is simply the space an object occupies. When scientific inquiry dictates a tie at this macroscopic level, we are forced to zoom in. We must stop looking merely at the space these liquids take up and start counting the actual stuff inside that space. We must transition our perspective from the macro to the micro. We know that acetone features a nonpolar carbon skeleton, which under normal circumstances would repel water. So what is a hypothesis? Master T. Our hypothesis must state that specific, highly localized intermolecular forces, namely, the hydrogen bonding we just noted, must be completely overpowering the general nonpolar repulsion of the carbon skeleton to achieve this level of miscibility. To test this and resolve our tie, let us meet contenders by looking at their physical metrics. Acetone, with a chemical formula CHO, has a molar mass of approximately 58 grams per mole, making it a heavier molecule. It has a density of roughly 0.79 grams per milliliter and possesses a large, bulky structural skeleton. Water, or HO, has a molar mass of only about 18 grams per mole, making it much lighter. However, its density is higher, at 1.0 gram per milliliter, because its structure is incredibly small and compact. This gives us a diagnostic insight. Acetone takes up far more space per molecule, while water is tiny and packs tightly. Conceptualizing size and space. To help conceptualize this difference in size and space, Let's use a container analogy. If you have a 50-gallon tank completely filled with bouncy balls and an identical 50-gallon tank completely filled with small marbles, do you have the same number of items in both tanks? Absolutely not. The volume of the containers is identical, but because the marbles are drastically smaller, vastly more individual units of marbles can fit into that exact same space. Okay, Master T. Conversely, look at water. HO is minimalist. Composed of only 3 small atoms, it is a compact powerhouse. It can readily move into tiny gaps and pack together with incredible structural efficiency. In a population race confined to a specific volume, water's exceptionally small size becomes its single greatest advantage. This brings us to the ultimate metric, the mole fraction. This is a chemist's true measure of a solution composition. While volume looks at space, the mole fraction ignores space entirely and asks one fundamental question. If we were to count every single individual particle in this entire mixture, which molecule possesses the largest actual population? When we actually calculate that population, we uncover the molecular majority. Because water molecules are so small and densely packed compared to the bulky acetone molecules, a 50 milliliter volume of water contains roughly 4 times as many individual molecules as 50 milliliters of acetone. When we count the particles, it is no longer a close 50-50 tie. It is a microscopic landslide victory for water. We can now officially resolve the paradox by contrasting our 2 viewpoints. On the macroscopic level, we have a 50% volume to 50% volume tie. But on the microscopic level, the true population is approximately 80% water molecules to 20% acetone molecules. Therefore, when evaluated scientifically by population, water is undeniably the solvent and acetone is a solute. The paradox is solved. Welcome to the Eastern Cape. This exercise highlights why we must value true scientific inquiry over simple, rote memorization. The scientific method exists to reveal exactly how matter behaves and interacts. Our terminology is merely a tool we invented to describe those interactions. My call to action for us as educators and scientists is simple. We must always prioritize the underlying molecular reality over the rigid, superficial enforcement of textbook vocabulary. To summarize our journey, Master T, let's review the macro-micro framework we followed. We began with an observation proving miscibility. This led to an anomaly where our standard rule failed. We forced a shift from macroscopic volume to microscopic counting, resulting in the discovery of the mole fraction population. And finally, we reached our conclusion, where the paradox was successfully resolved. Thank you, Master Q, and the house. I am gonna bow out now.